Hello everyone, welcome to our presentation.
We're participating in the Future Engineering category for the WRO competition.
We created a autonomous car for competition.
I am Jerry and I am a senior at Western Christian High School.
I'm William and I'm a sophomore at Rancho Cucamonga High School.
I'm Harry and I'm a junior from Rancho Cucamonga High School. As you can see, this is our autonomous car model for the competition. It's a combination of both hardware and software.
We mainly use a Raspberry Pi, which is a single board computer.
We also use convolutional neural networks to predict images, Donkey Kong forums for our base code, and TensorFlow to train our AI models.
As you can see here, we are currently in the process of training the robot. What we do is we control the car by using the joystick manually to collect data.
Then we will use the data collected by the car to train an AI model using TensorFlow and implement the model so that the robot will be able to navigate the track by itself. Our hardware design integrates innovative modifications to maximize the performance of our truly autonomous vehicle. Here is an overview of the critical aspects.
The car is powered by an external battery, which drives the donkey car cases. This setup ensures the car operates reliably and can handle the demand of continuous AI processing. Another external battery provides the consistent power to Raspberry Pi with in turn power motor controller and other peripherals. We made a precise modification to the gear system of the car. The gear now correlates the voltage data directly with the car's moving direction. Positive voltage drives the car forward, while negative voltage enables reverse motion. This synchronized provides consistent control feedback for the AI model, which improving the overall response and performance of our car. To improve the maneuverability, we cut away the section of the bumper. This modification allows the front wheel to achieve a greater turning angle, which enables the car to navigate tighter turning on track with increased precision. The car design incorporates a camera and a controller as primary input devices. These components work seamlessly with Raspberry Pi to collect essential training data, such as image and control input. This data forms a foundation of training our AI model. The trained AI model is deployed on the Raspberry Pi and uses gyro sensor and camera input to make real-time driving decisions. The model's output is translated into precise WPM signals, which control the steering and throttle mechanism that ensure the smooth and accurate vehicle's operation based on AI predictions. The hardware modification reflects a focus on adaptability, efficiency, and integration. Each change was made to improve the vehicle's ability to collect actual data, navigate to track efficiency, and execute AI drive tasks with high reliability.
In summary, the hardware serves as a robust foundation for the seamless integration of the software and AI components of our vehicle, which allows it to perform efficiently and optimally in dynamic conditions.
We will now be talking about the software part of our solution. Most of our software are written in the Python coding language, and it is stored in an SD card on our Raspberry Pi.
The program being shown on the screen is manage.py, the main program for our RC car. By running the program in the Raspberry Pi terminal, we are able to run the vehicle manually and record data that we can later train for our AI model. Included in the program are other important functionalities, such as deleting incorrect data and sorting timestamps and images. Another important program on our RC car is config.py, where all of the vehicle controls are done. As you can see here in config, we are able to set our throttle values and steering values for the PWM. This is to ensure that our vehicle is functioning at the best capabilities. Calibrate.py is an important piece of code where we simultaneously try to input various pieces of information at the same time while cooperating with each other. Think of this as trying to cook a large meal in which you might do multiple tasks at the same time, like boiling the water, cutting vegetables, and frying your pan. This program is extremely important in making our vehicle process information quickly. Moving forward, we have airc-drive10.py, a program intended to be implemented in the final run of the competition. The program receives the AI model that we have trained and uses it to run the track. In it, we can do various adjustments such as ramping up the speed of the car or changing certain models that fit better. To change the particular model used, we have to make sure the model is in the files folder and we just change the name of the input.
Overall, all of us software assimilate with each other really fluently and provide us an easy navigation experience and a fluid training process.
There are 4 key components that allow us to train our AI model: VNC Viewer, TensorFlow, Donkey Car, and FileZilla. So what FileZilla does is allow us to transfer files from the Raspberry Pi onto our computer for training. TensorFlow is the actual program that trains the AI model. VNC Viewer allows us to remotely access the Raspberry Pi using our computers. And finally, the Donkey Car is acting as our base code for all the stuff we run. So our data will be recorded using a joystick, as you see here, and then we'll be driving circles around the track, and the data will be recorded onto the Raspberry Pi. And as you can see here, we have our folder, it's in my car, and all the data I just recorded will be sent into the data file in the Raspberry Pi. So like all the image data, let's say this one, it'll be shown, and then we later use all this data to train the AI model.
Second, we have to transfer the data out of the Raspberry Pi into our own computers. To do this, we use an application called FileZilla. We must connect to the Raspberry Pi through the IP address and transfer the files. In this case, the IP address is 192.168.1.89, and we connect using the password of the Raspberry Pi. This process usually takes around 30 minutes on a normal laptop, and with the addition of a GPU, our group is able to transfer these files in a matter of seconds, which greatly improves the speed of the training process. And as you can see here, I'm demonstrating how to transfer the files. Third, we will gather the transferred files into named folders that we can easily access in our downloads. To do this, we will have to put our files in a folder called My Car in our user folder so the training software can find the file. As you can see here, what I'm doing is I'm transferring the models into the My Car folder, and then I will be copying and pasting it into the section.
We now must access a command prompt called miniconda3 to access TensorFlow and train our data. So what we will do is we paste this line of code here, and then we start training the data.
The code will execute the software and start to train the data, usually taking between 30 minutes to an hour, but can be accelerated by using a computer GPU. In our case, after training 7 sets of data, we took around 2 hours.
Once we are done training the data, we export the AI model back to our Raspberry Pi via FileZilla, and then we can run the imported AI model using ARC Drive 10 on the map here.
The competition is organized into 3 different categories: the Open Challenge, Obstacle Run, and Special Challenge. The goal: to complete the challenge with as much accuracy and speed as possible.
The Open Challenge is the most simple run where the robot has to complete 3 laps around the track. The middle barriers can be shifted to create a greater challenge for the participants. The direction is determined by a coin flip during the competition and can either be clockwise or counterclockwise for all 3 runs. The maximum amount of points is 30 points. The second challenge is the Obstacle Run and is the most complicated out of the 3, with a maximum of 70 points. The Obstacle Run can be viewed as 3 parts combined together.
The first part consists of driving around the track while dodging obstacles, but with a twist. The robot must turn right to avoid the red obstacles and turn left for the green obstacle.
The second part consists of after 2 runs. The robot needs to detect whether the block in front of it is red or green. If the block is red, the vehicle turns around and compete at another lap with Obstacle Run. Green makes the vehicle go another lap in the same direction.
The third step is to finish the lap and attempt to park the vehicle into a purple slot. The obstacle rules don't apply, but the robot still isn't allowed to hit the rules.
The final challenge is the surprise rule, which is an on-the-spot coding session that involves rules that are denounced at the international final. Not much is known except for all the coding is completed at the venue and no outside interference is allowed. The maximum points are unknown.
Finally, there is a GitHub documentation with all the design process and information for the vehicle, max of 30 points. Overall, each challenge provides a complicated series of events that test knowledge and ability of the students.
So here are the hardware limitations of the robot. It cannot exceed 30 centimeters, 20 centimeters, 30 centimeters, and it has to weigh less than 1.5 pounds. And as to what it can be consist of, there are no limitations. It can be Legos, Arduinos, RC car, and etc.
Thank you for watching our video. DriverUS